Professor Tyson
Okay.
from University of Illinois at Urbana-Champaign. So good morning, Professor. He will talk about geometric measure theory and Fourier analysis in the sub-Riemann Heisenberg group. So Zoom stage is yours, Professor.
Thank you very much. And yeah, I'm very pleased to be a part of this. Thank you to the organizers for the kind invitation to participate in this conference. I'm sorry I haven't been able to be a part of so much of the conference so far. The time zone difference is pretty substantial for me. I believe today's talks for me started at 1 in the morning, but I'm very pleased to be here. I'd like to talk a little bit about some recent work in geometric measure theory in the sub-Riemannian context, particularly in the Heisenberg group. So I'll talk about a circle of ideas in this area with some connection to the non-commutative Fourier analysis, although that part is very much still quite preliminary, but I hope it'll be somewhat interesting still. So let me start maybe with a brief outline just to mention where I'd like to go with this. So I'll begin, I think, very quickly by reviewing the Euclidean background to try to set the stage here. So the basic type of question that I'm interested in is to understand the effect of various types of mappings or transformations on Hausdorff dimension of sets, connections to the geometry of sets and measures, the rectifiability, densities of measures, and so on. So I want to sort of briefly recap some of this in the Euclidean context, and then move to a series of results in the Heisenberg group equipped with the canonical sub-Riemannian structure. There's some older work that I want to talk about on projection mappings. Here the question is really to understand what's the right notion of projection mappings in the Heisenberg group, and then how do these mappings affect the dimensions of sets. This is all related to rectifiability, and there's a long-term project to understand perhaps how to characterize rectifiability through projection mappings or densities of measures. So I'll say a little bit about that. And then at the very end, very briefly, suggest an approach via Fourier analysis, Fourier coefficients approach, which well, the material that I'll talk about was developed by my student, Fernando Roman Garcia, in his thesis this year, but this is all very much still work in progress. So this is the basic outline. And if there are any questions, so this, please feel free to ask. I'm happy to stop and take questions along the way. Okay, so as I said, very briefly, let me start by recapping, telling the Euclidean story here. So the basic question is to understand as I said, the effect of mappings and transformations and other operations on the Hausdorff dimensions of sets. This is a long-standing and classical problem or sort of program in geometric measure theory. So maybe the origin of a lot of this is the classical projection theorem of Marstrand and Mattila. So let me denote by G and M, the standard grasmanian. These are M planes in Rn, and it comes with a canonical probability measure that's invariant under the action of the orthogonal group on G and M. And by P sub V, I just mean the classical projection, just a projection from Rn into an M-dimensional subspace, a linear subspace V. So the question is to understand how projections mappings affect the dimension of sets, and we're looking for a generic result, a result that's perhaps with respect to almost every projection mapping quantified with this probability measure gamma n m. So the theorem is that the borderline case is M itself. If the original set E has dimension less than M, then almost every projection preserves the dimension of the set. And if E has dimension strictly larger than M, then almost every projection has positive measure. Here, HM is the Hausdorff, always throughout this talk, HM will be the Hausdorff measure. And of course, so everything here is just a generic statement with respect to this measure on the grasmanian. Marstrand proved this originally in the plane. Bob Kaufman introduced this sort of energy technique here, and then I think Mattila gave the full result in Rn. I want to talk briefly about the energy method and how this ties into Fourier analysis. So by the S energy of a measure is just this singular integral where I take the integral with respect to the measure mu and integrate this kernel, distance between the points to the minus S. And the connection here to the Hausdorff dimension is Frossman's lemma, which has a couple of versions, but the energy version is that the dimension of a set is strictly bigger than S if and only if there's a measure supported on the set E with finite S energy. So this lets one turn the question about distortion of dimension into a question about distortion of energies. If you push forward a measure under the mapping, one can try to quantify the effective mappings on energies. So Kaufman's proof of this projection theorem, this is in low dimensions, when S is less than the dimension of the subspaces into which we're projecting, is just to prove that these projections preserve the finiteness of S energies. And this is a fairly simple computation. You integrate over the Grasmanian, apply Fubini theorem, the change of variables. It's fairly straightforward. This all has there's a Fourier approach as well, because these energies of measures can be computed on the Fourier side. So I'm going to write by mu hat here the Fourier transform of a measure. I'm being a little imprecise here about the exact choice of the Fourier transform, where the 2 pi should go. So I just write like this. The Fourier transform, the distributional Fourier transform of the kernel that shows up in the energy is another kernel of the same type, which is conjugate with respect to the dimension of the ambient space n, so it's kn minus s. And then it's a simple computation to calculate the energy of a measure on the Fourier side. And the answer is it's a dimensional constant, depends on the dimension of the ambient space n and on s. And then there's the integral on the Fourier side of kn minus s, so that's the transform of ks, and then the norm of mu hat squared. On the other hand, if mu hat is in L2, then the original measure has an L2 density with respect to the big measure. If mu hat's in L1, it has a continuous density. So this gives ways to approach this kind of question on the Fourier side. The second part of the theorem, when S is bigger than M, if one starts with a measure with finite M energy and does the same computation, you find that the Fourier transform of the projection of the measure, it generically lies in L2. So the projected measure is absolutely continuous with respect to Hausdorff measure on the linear subspace V with an L2 density, and the support's going to have positive measure. And again, that's almost every V. And a similar argument, this is more recent, shows that if E has a dimension even larger, then the Fourier transform of the projection is in L1, so it has a continuous density, and this eventually shows that the projection actually doesn't just have positive measure, but actually has non-empty interior. Okay, so that's kind of a very quick introduction to these projection theorems. Let me say a little bit about rectifiability and density, because that's the next other thing I want to talk about in the Heisenberg setting. So the theorem distinguishes between, whether the set has dimension larger than M or smaller than M. The borderline case is very subtle. And here the main result is this SpecikovicFederer theorem. If E has dimension equal to M, where M again is the dimension of the subspaces into which we're going to project, then whether or not the projections have a vanishing measure is a characterization of rectifiability, or in this case, unrectifiability of the set. So I just remind you quickly that a set in Rn is M rectifiable if essentially it's a union of Lipschitz images of subsets of Rm, and unrectifiable if it sees no positive measure Lipschitz images of subsets of Rm. And this is a dichotomy for subsets of Rm. The M rectifiable sets in geometric measure theory are essentially the analogs of smooth objects in differential geometry, smooth M manifolds. And there are lots of different characterizations of rectifiability in terms of approximate tangent spaces, in terms of integral geometry. But the one I'm interested in is the characterization of rectifiability via densities. The density of a measure, the S density of a measure, is just the local behavior of the measure relative to the radius to the power S. So if this limit exists, we call this the S density of mu at X. And Preiss's theorem states that the existence of the density is a characterization of rectifiability. One direction here is very easy. If a measure is supported on a smooth M manifold, it's very easy to see that this density exists, the M density, and more generally if the support is M rectifiable. But the deep part of Preiss's theorem is the converse direction. If the M density exists, then the support is in fact a rectifiable set. And we only restrict here to integer values M between 0 and n, and that's the first part of the theorem, which is due to Marstrand. If the S density exists in a set of positive measure, then S has to be an integer. And very briefly, I want to mention the role of uniform measures in this, in the proof of this theorem. A uniform measure is a measure with the property not just, well, I'm not asking here this limiting statement, but I ask that the measure of every ball supported in the set of every radius is a fixed constant times the radius to the power S. So for instance, Lebesgue measure obviously is an n uniform measure. Hausdorff M measure on a linear set is an M uniform measure. The way that these arise in the proof of Preiss's theorem is fairly clear. If you blow up a measure, take what they call a tangent measure. So a tangent measure is a weak star limit of rescaled and renormalized measures where we zoom in at a point with smaller and smaller radii. Then if the density exists, then these tangent measures will in fact be uniform. They'll have a more scale invariant and global condition. And so one wants to know which are the uniform measures. In low dimensions, these uniform measures are just the flat ones, the ones which are supported on linear subspaces, but it turns out these are not all of them. So Preiss showed that Hausdorff 3 measure restricted to this quadratic variety, the light cone in R4, is a 3 uniform measure. And in fact, there's a characterization of all codimension 1 uniform measures. Even in Rn, in the Euclidean case, there's no full characterization of uniform measures in arbitrary intermediate dimensions so far, although there's been some recent work in that direction. Okay, so this is the circle of ideas in the Euclidean context. I want to talk about how some of these results extend to the sub-Riemannian Heisenberg group. The projection theorem work, as I said, is older work with my collaborators Zoltan Balogh in Bern and Pertti Mattila in Helsinki, Durand Cartagena and Katrin Faessler. And the density and classification of measures is more recent work, which combines some work of mine also with work of a student in Italy, Andrea Mero. And then finally, a suggestion for how to use the Fourier coefficients approach to compute energy integrals in the Heisenberg group. All right, the Heisenberg group, and I know this is fairly standard for everyone, so I'll go quickly through the background. I'm going to model the Heisenberg group with this symmetric model, so Cn cross R with the group law, where the final coordinate is twisted with this symplectic form omega of Z and Z prime. The horizontal structure is what defines the sub-Riemannian geometry of the Heisenberg group and induces this Carnot-Carathéodory metric. So we get this by taking a left invariant structure on the Heisenberg group. I fix a standard basis at the identity at the origin of the space and then push this around by left translations to get a left invariant framing of the tangent bundle. If you restrict only to the first 2 n directions, the ones that live in this Cn direction, you get the horizontal bundle. This induces a metric in the usual way by minimizing lengths of horizontal paths connecting points. But we tend to work with this Koranyi metric, which is a more computationally tractable metric. It's bi-Lipschitz equivalent. So for the purposes of computing Hausdorff dimension, the Koranyi metric is a standard one. How to understand what projection mappings should be. This is what I want to spend a little bit of time on. To understand projection mappings, I need to understand what are the natural analogs of linear subspaces. And the appropriate analog here are homogeneous subgroups. So these are subgroups that are closed under the dilations. So the dilations of the Heisenberg group are these anisotropic dilations. They dilate in the first coordinate with R and in the vertical component with R squared. These scale these metrics by factor R. And there are 2 different types of homogeneous subgroups, vertical and horizontal. They have very different properties. The horizontal subgroups are the ones which live in the first layer. And because of, if this is going to be a subgroup closed under the dilations, it needs to correspond to an isotropic subspace in the first layer. This is a subspace which is annihilated by the symplectic form that I wrote down. On the other hand, there are vertical subgroups where I can take any subspace in the first layer and take its product with the vertical direction. The isotropic subspaces only exist in low dimensions up to half the dimension of the first layer, up to n. So remember, the first layer has real dimension 2n. The metric in this, either of these metrics in this context is just the Euclidean metric. These subspaces are just isometrically embedded copies of Rm. The sub-Riemannian dimension and the Euclidean dimension are the same. The vertical subgroups, in the vertical subgroups, the metric is not the same as Euclidean one, and there's a dimension jump, which comes from the fact that the vertical direction does not have a Euclidean structure. Where do the mappings come from? If I fix a horizontal subgroup, so again, this is a subspace in the first layer, an isotropic subspace in the first layer, there is a complementary vertical subgroup obtained by taking the Euclidean orthogonal complement in the first layer and then also the t direction, the vertical direction. And this induces a semidirect decomposition, a splitting of the Heisenberg group. So this is a semidirect product decomposition with the vertical and the horizontal subgroups. There are two ways to do this because it's non-commutative. We take the one where the vertical subgroup is on the left. This is geometrically natural because it means that the left cosets of the vertical subgroup are all isometric to each other. So this defines mappings of the Heisenberg group into the horizontal and vertical directions just by reading off the two components in this decomposition. And you should think of these as projection mappings. They're quite different from each other. The horizontal projection map has a character very similar to the Euclidean one. It's linear map, it's a Lipschitz map, it's a group homomorphism. The vertical projection maps are quite different. They're nonlinear mappings with respect to the underlying coordinates. They're not Lipschitz maps, they're not group homomorphisms. But geometrically, these are natural ones to consider because the fibers of the vertical projection map are the ones which are as I said, left cosets of horizontal spaces. And so the question is to understand how these projection mappings affect Hausdorff dimensions of sets. So let me just briefly show a few of the results. So this is older work with my collaborators where we just use the energy methods only and sort of an ad hoc approach to compute these energy integrals. So first, there's a sort of universal statements, how these projection mappings affect dimension. The formula is a little bit complicated here, but what I want to say here, so I take a fixed subset of the Heisenberg group with fixed dimension, I take a vertical subgroup and ask, how can these projections, what's the largest and smallest values that the projections can have in terms of the dimension? What we're interested in, as I said, are generic statements with respect to some version of a Grassmannian. The Grassmannian here is so-called isotropic Grassmannian because we only consider, as I said, isotropic subspaces in the first layer. So so fixing M between 1 and n, the isotropic Grassmannian is a subset of the full Grassmannian, G2NM. It corresponds only to isotropic subspaces. This is the parametrizing space for either of these two families of subgroups. It comes with its own invariant probability measure. And so in terms of dimension distortion by generic projections, what we're able to prove is a lower bound on the dimensions of projections in the generic context, but only in low dimension, the dimension up to 1. There have been some slight improvements of this in the first Heisenberg group more recently, but we still are far from a complete understanding of the generic distortion. There's some hope that, you know, different tools, for instance, Fourier analytic tools might have some implications for that. Let me go on to talk a little bit about density, rectifiability, and uniform measures. So as I mentioned, in the borderline case, rectifiability and unrectifiability comes into play. And in terms of Preiss's theorem, there's a connection to the classification of uniform measures. Our initial result here was just to prove Marstrand's theorem, to prove that a measure which has a density with respect to some exponent s, the exponent must be an integer. There are several proofs of Marstrand's theorem in the Euclidean case available. And in this particular context, we adapt a proof by Preiss and Kirchheim, which uses the fact that the Koranyi metric is semi-algebraic. We don't know if Marstrand theorem holds for the Carnot-Theodori metric in this context. So this is the reason for the use of the Koranyi metric here. A big distinction here with the Euclidean case, the exponent s may not be the topological dimension of the support. In fact, it's going to be the Hausdorff dimension, which may be either the topological dimension or one more than the topological dimension, depending on whether we're in this horizontal or non-horizontal case. For the classification of uniform measures, our recent work, we've been able to do this in the first Heisenberg group only, and the answer there is, as in the Euclidean case, that there are no exotic or non-standard flat measures. All the uniform measures are flat. That is to say, they are the appropriate Hausdorff measure restricted to one of these horizontal or vertical subgroups, or a left coset of such a space. We're still maybe a challenging question here is to know whether there's an analog of the full Preiss density theorem to really characterize the density of measures in terms of rectifiability. This is known in the lowest dimension, dimension 1, in any metric space. That's old work of Preiss and Tischer. And Merlot's work shows that this is also known now in codimension 1 in the Heisenberg group. But the intermediate cases are open. So an obvious case, for instance, is in the first Heisenberg group to consider two densities of measures. Okay, so in the last few minutes of the talk, I want to talk briefly about a Fourier coefficient approach to computing these energy integrals. This is the work of my student, as I said, Roman Garcia, in his thesis this year. This is still somewhat preliminary, but it gives some sense that I hope that the sort of non-commutative Fourier, group Fourier transform may be useful in this context. The project that I gave to him essentially was to try to understand the relationship between the group Fourier transform and geometric measure theory in the context of the sub-Riemannian Heisenberg group. So this part I hope will be, the background here I think is probably familiar to many people here. I'll have a few slides to briefly recall the strongly continuous unitary representations of the Heisenberg group. Here we're using this symmetric model for the Heisenberg group. So these representations rho lambda act on functions in L2 Rn. I'm sorry, there should be bounded operators on L2 Rn. My apologies. So the group Fourier transform of, in this case, the function f on the Heisenberg group, then can be thought of as an operator valued mapping. It takes in this parameter lambda and returns a bounded linear operator on L2 of Rn given by integrating f against the representation. This is a vector valued integral, maybe in the sense of, yeah. So as usual, this converts convolution into composition, where the convolution here is the group convolution in the Heisenberg group. It maps L2 to this non-commutative Hilbert space L2 of R star into the class into S2, the Hilbert-Schmidt operators, and there's a Plancherel theorem. This group Fourier transform extends to measures, just as the Euclidean one did. So the Fourier transform of a measure on the Heisenberg group, in the same way, I integrate the representations acting on phi, but this time with respect to a measure mu. Again, there's the connection between the convolution, this time is convolution of a function with a measure, and composition on the Fourier side. So one might ask whether integrability of the Fourier transform of a measure relates to some density properties of the original measure itself. The same type of theorem is true, and this is part of Fernando's thesis. If mu hat is in L2, then mu is absolutely continuous with respect to the underlying measure in the Heisenberg group with L2 density, and there's a corresponding statement in L1 with continuous density. If one wants to try to apply this to the problem in geometric measure theory, then we'd have to be able to compute energy integrals, and this means we need the Fourier transform of the Koranyi kernel of the k sigma of p. This is the Koranyi norm to a negative power. Of course, this Koranyi kernel doesn't lie in any natural LP space, so we would need this in the sense of tempered distributions. And so here there's an approach to the group Fourier transform via Fourier coefficients, which Fernando used. This is work of Bahouri-Chemin-Danchin. Using a Hermite basis, the Fourier domain comes out in this case to be n to the 2n. So there's sort of a 2n tuple of natural numbers, and r star, this is the parameter lambda. It's endowed with a measure, which is counting measure, of course, in the discrete part, and then this Plancherel measure on r star. And the Fourier coefficients you get in the usual way by acting with the Fourier transform in the basis. So this computing coefficients in this basis. So this writes the Fourier on the Fourier side, a mapping on the dual space Hn tilde, and suggests that there's going to be some way to sort of formulate the energy integral in this context. The distributional transform of the Koranyi kernel has been computed in the past, but now we can write it in terms of these Fourier coefficients. And the result is that the Fourier transform of the Koranyi kernel, kq minus sigma, is a dimensional constant, and then there's an explicit expression in terms of both the, so it lives only in the diagonal when the alpha and beta are the same, and then there's an explicit coefficient in terms of lambda and alpha. And if we denote this entire expression that shows up here with k sigma of a point in the Fourier side, then you get an explicit expression for the energy integral in frequency space. And this is the result from Fernando's thesis, that the energy integral, the S energy, or the sigma energy in this case, of a measure mu on the Heisenberg group can be written, there's an explicit dimensional constant, I don't write the value here. There's an integral on the dual side of the kernel multiplied with the norm of mu hat squared. So this is a direct analog of the classical Euclidean formula, right? For a measure in Rn, the S energy was written this way, and suggests that we may be able to use this type of expression to actually start to compute and estimate these energies, and especially the distortion of these energies under various types of mappings or transformations. So this is ongoing work. I don't have results to report here, but obviously we're interested in applications to the vertical projection theorem from before and trying to improve our previous results. But there are other ways in which the energies of measures have been used in geometric measure theory. One well-known one is the distance set problem, Falconer's distance set problem, which asks how large does a set have to be so that the set of distances between points in the set has a positive length. And this one looks fairly promising by computing the push forward of the energy of the push forward of a measure under essentially the distance between points. And then there are also intersection theorems in geometric measure theory. You take two sets, move one of the set around by rigid motions of the space, and ask what's the dimension of the typical or generic intersection. And all of these in the Euclidean context have been attacked using these energy methods and the Fourier approach. And so these are all potential applications of this type of Fourier equation approach to the energy integrals. So that, I hope it's just, as I said, some type of general introduction to and a potential use of Fourier methods in the context of geometric measure theory on the Heisenberg group. And time is up, so I will thank you, and I'll stop here. Thanks very much.
Thank you, Professor Jeremy Tyson, for an interesting talk. So please, any questions?
If I may?
Yeah.
Professor Tyson,
Yeah.
My question is about this Fourier coefficient approach to energy integrals, because I know that some problems in theory of geometrical theory of measure are related with the sign restriction problem. Then maybe here also similar connections, or in the case of the Heisenberg group.
That's right. Yeah, I think this is, I mean, I think there are a large number of problems where this sort of, I think this is a good point.
Okay.
Thanks.
Thank you.
So, any other questions?
I would like to ask something.
Yeah.
So why do you know so much more in the case of H1 than say Hn? Or at least that's the impression I had. I'm sorry if I'm wrong.
Well, I guess I can give two answers to that question. One is that the methods we use somehow up to this point have been essentially ad hoc, right? So this energy interval can be written down explicitly. It's just the underlying space is a Euclidean space. The group law and the metric and so on allows you to just write this thing down. It's a fairly complicated singular integral with a kind of nonlinear denominator here. And one just tries to attack this by purely ad hoc methods. This is sort of technically complicated. And in the first Heisenberg group, well, it's somehow a little simpler to just sort of start to attack this. That's one answer to the question. Another one is that even in the Euclidean case, in high dimensions, there are some unusual features that show up. So for instance, the existence of these exotic non-flat uniform measures and so on. And in high dimensional Heisenberg groups, the same things must arise because, in the Heisenberg group Hn, there's an embedded isometric copy of Rn in the horizontal direction. So the complexity must be at least as complex as it is in Rn. But in the first Heisenberg group, somehow everything is much simpler from that point of view. So I think maybe those are two different answers to your question.
Yeah, okay. Thanks a lot.
Yeah.
So any other questions? Yes. So maybe I would like to ask about, are you planning to extend to H-type groups or some Carnot groups? This kind of
H-type groups would be an interesting direction. I thought about this maybe for the quaternionic Heisenberg group or something.
Quaternion. Yeah.
For general Carnot groups, so let me say for the projection mapping story, what's important there is that there is a Lie group. There's a continuous group's worth of projection mappings, right? So these things are parameterized by this Grassmannian manifold of isotropic subspaces. Because you want to prove something generically, so there needs to be somehow a positive dimensional worth of mappings of this type. And this comes from the symmetry of the Heisenberg group. The fact that the isometry group of the Heisenberg group with either of these metrics is a positive dimensional Lie group. In this case, it's a unitary group. If you have maybe a more complicated Carnot group that doesn't have these internal symmetries, then it's not really clear how to say that, what's the correct family of mappings parameterized by some space. So I don't know how to formulate the projection theorem in that context. Some of the other problems might make sense. For instance, the classification of uniform measures and so on. This is just a specific problem, could make sense in more general Carnot groups. In H-type groups, absolutely. This is a very natural question to ask. I haven't tried this in the quaternionic Heisenberg group, but I think one should be able to do something there.
Okay, thank you. I think that's all.
I think another question, maybe.
Oh, yeah.
Sir,
Hi.
As Falconer's distage conjecture is not solved for general sets.
General sets or general
any
spaces?
general sets, general spaces. In Rn also, that is not solved for general sets.
It's not even solved in Rn, of course. That's right.
Yes.
There are estimates, but in high dimensions.
Are you solving that for any particular sets like self-similar sets or self-affine sets?
We're only really just starting this. So you mean in the context of the Heisenberg group?
Yes.
This would be one question to ask, if it's possible to do this just
because there is a large number of literature on Falconer's conjecture.
Yeah.
And that has been solved for self-similar sets, self-conformal sets, and self-affine sets like that. So that's why I wanted to ask about that.
Thanks. That's a good suggestion. And I mean, there is now a reasonable theory of self-similar and self-affine sets in the Heisenberg group as well, with respect to the sub-Riemannian structure. So this is a good idea. Thanks.
So, any other questions? Okay. Again, I would like to thank you for your interesting talk and
Thank
the
you. Thank you.
discussion of questions. So I will pass last word for today to David.
Yes, well, I mean, there's not so much to add, except for the fact that we've been listening to very interesting talks again today. So thanks again to all the speakers and all the chairs also. And yeah, I don't know if anyone would like to continue discussing a little bit, then we'll stay online, unlike yesterday. And yeah, to all the others, have a good afternoon or morning or good night, depending on where you are. And see you tomorrow at 9 Central European time. Yeah, and then I think we can just stay a little longer and then. Yeah, I had another question for Professor Tyson, but what was that again? Yeah, so one suggestion, if you're looking for, say, a relatively, okay, so maybe H-type groups are simpler, but say, in the 90s, there was this paper by Folland where he studied meta Heisenberg groups. And so you take the same construction as you normally apply to get from Rn to say Hn, and then you get to a 3-step nilpotent group. If you start with a, what does he call it, a completely non-abelian group, a nilpotent group of step 2, say. And if you do this for the Heisenberg group, then you get a 3-step nilpotent group of one-dimensional center. And there is a very explicit description of the analog of the metaplectic group. So I don't know if that's interesting to you, but maybe there you see which sort of isometries you have.
That would be the first
group
question.
automorphisms, yeah. So.
Yeah, right. That would be the first question to ask. How rich the
So
isometry
maybe, I don't know if that's
is.
an interesting example to look at, but there you know what the automorphisms are, and they're.
It could be actually. Yeah, if you have do you have a reference for that? It would be.
Yeah, I can send you the paper.
That'd be great.
Yeah.
Thanks. Yeah.
I mean, just because I don't know, I just thought an explicit example might be interesting in say other cases. Then.
Absolutely. Yeah.
I mean, just in answer to your answer to the question, what about Carnot groups? So that's why I thought.
Right. Thanks. I'll also send the slides along. I should send them to you or something to post.
Yeah.
I know it goes fast.
Thank you.
David?
Yes?
I have a question to Professor Jeremy Tyson.
Yeah.
Yes, please.
Hello. Yeah.
Is there a preprint on this work? Preprint of your student's thesis and some parts of this?
Yeah, there is, I believe, on the archive.
Oh, okay.
It has
I will look at.
Yeah, I mean, the title is, I think, fairly descriptive. It's probably exactly what I said, a Fourier coefficients approach. So, yeah.
Yeah.
Maybe if
I see if I can find it. Put it in the chat.
Okay, great. Thank you. I guess I also would find it by the name of your last name.
Roman Garcia. But let me find it. Since we're on here, I'll find it right away.
Maybe I'll send you the paper that I was talking about.
Very curious, this approach with the Fourier coefficients. Or
what? Okay, I sent through the chat. There is the link to the archive.
Thank you very
from
much.
my student. Yeah.